presentation, I hope. My name is Oleg, Rostov, South Federal University. So, my presentation is about the quick restoration of the murky image by a revolving camera. So I decided to add some miracle and tricks into my presentation. For a start, let us compare between the maps cards or cards and a camera, revolving camera. The camera gets a new image, but after the full circle, it starts repeating. Same goes to the cards. We can just shuffle the cards as much as we want, one after the other. But when we have a complete circle, the cards will repeat. Let's take some image, any image here. In this case, let's take this one. And as you can see, when it was dropping, you couldn't see well. Same thing could happen if the camera was shaking or the image was shaking. You see, I'm moving, you cannot see so well. You get the blur. Once I move faster, the blur is stronger, and it can turn into something else. And what can we do with it? So, what is this blur? This blur is just overlapping of different images, and it depends on the speed of the camera revolving. So how do you address it? So the math part is that this system of linear math equations with this circulant matrix. So you couldn't fail to use this special feature of the circulant matrix. It means that the next line is different from the previous one with the deviation of 1. So I shall try to explain where's the difference. If we don't shuffle but just move, so the sequence doesn't change. So some cards tricks are based on it. For instance, some variable arbitrary card will be put next to the card that the man knows. So then we see that the lines are very slightly different. So the speed of a solution is a very important factor. For instance, in case of image recognition, the faster we remove the blur, the faster we recognize the images. So you can use it in for drones or some artificial intellect system, so who use a computer vision. So, and I shall try to show you what's the speed. What is the speed? Imagine you select some arbitrary card, a card. If we remove it someplace to the middle, then we have a chance to look for it. We can actually shuffle the card, and there will be a moment when we get the necessary one. But we would like to have an algorithm so that you can find this necessary card through a click of the fingers. And in this case, we would like to have an algorithm that just click your fingers and you get it. So, and then what we can see the error in the raw data and the calculation. For instance, our camera puts 8-bit for the color of a pixel. And in this case, we have the digression of 2 by a factor of -8. And even with a slight blur, the quality of the restored image may not be acceptable. Look, for instance, we have this original, and then we get that one. So it happens. But you see that this blur is not very strong. It's from 43 to 47, but the quality is actually visible. If we take 50 plus, but that's not the only factor that influences the quality. So in this case, we put 16-bit to the color of the pixel, and we see two pictures. One of them is worse and another is better after restoration, but we use the same algorithm. And the picture on the left was gotten from the blurred picture with the blur higher than the one for the that's the original for the right picture. So it means that the blur was higher, but the quality became better. The restoration is better. And so there is a special parameter, that's the number of prerequisite or whatever. So in this, for these two pictures, it is very different, by 1,000 times different. So let's talk more about the prerequisite number. So it shows how many times the deviation of the raw data is different from the final data. So we got a formula to find this number. Depending on two parameters, the matrix size and the blur size. And this formula allowed us to build the chart for this very number that shows the number at the fixed matrix. So we understand from this graph that some slight change in the blur may give us a different number. It means that we can take and speed up or slow down the camera to make it faster or slower, and it will give us the lower number and the result, the final result, better. And we developed an algorithm with some parameters that we can see here, and it is my final slide, and I wanted to try to show how this algorithm works and operates. And let us try to select some arbitrary image. Just say stop at any moment. I can keep I closed my eyes and just, you know, your image, and we shall just shuffle it so that we couldn't find it easy. I shall use the algorithm now. For our algorithm, what do we require? We need the blur image. So I shall take a joker. I'll give it to you and just put it in any place between the cards, and please cover it with your palm. And we shall use this algorithm. Now I clicked, and you will know what image it was. So that's approximately how it works. I thank you very much. If you have questions, thank you. So about the math. Yeah, very good, robust scientific presentation questions. Just magic. Yeah, magic always mixes with science. In the training process for students, we use similar methods. They help to get them interested. I have a question. At some images, you demonstrated the algorithm, but how do you address the task of adequate evaluation? Is there some kind of database for images that you used? How other algorithms work good or badly? So more formal estimation. I understand your question, but it's much better that a person, another person will respond. Thank you. So
Mr. Kozak developed it and helped. So there've been many stakeholders. We've been trying just to do the fast algorithm. So there are two ways to achieve the goals. You can take an algorithm, a good quality algorithm, and try to transform it. But we decided to take a different way. So we took a simple event, and then we got so even faster than the Fourier transformations as for each pixel. So we had 4 operations, and the Fourier translation, which is m times constant, so complex numbers. So we took this algorithm and made it very fast. And so how we do that? The matrix is very specific at the matrix, and that's why we managed to find so quick and efficient algorithm. So we found it for an event when the matrix is there. So then there is a eroded matrix for uneroded matrix. So the program has not yet been implemented. So we've done it for uneroded matrix and now for eroded matrix. So then parallelization has not been used. So we have not paralleled it because we know what Yuri Panchin told us about today, and we're aware of that. Said then good processors, modern processors, so the time of access to memory and vis-a-vis time to process of the data, sometimes it's up to 100. So then that's why to calculate you can fast, but the bottleneck is to transmit data. You have 4 operations per pixel. That's a characteristic. It's a property. IBM refers to it as a flop is filled in. So the number of operations divided by the volume of data. And so when this ratio is 4 to, it's not a reason to parallel it. But at the same time, so while we download it and took the blur off, and so then the data is in the cache, you can start to process it right away. So when they have just taken in the blur and then start identifying it, or just we can just look for other mistakes and errors. So for example, so with the camera that turns away, array.
Очевидное вроде бы применение это поисковые какие-то задачи, да, то есть по некачественному изображению найти ту, которая более качественным является. Это вот вы как-то эту возможность?
Ну, я думаю, мы к этому придем. Пока что ситуация такая. Камера вращается по кругу горизонтально, и смаз создает искусственно. Бывает, но все равно. Или мы в момент, когда нас фотографируют, там махнули рукой или повернули голову, и тогда смазанное изображение получается на фотографии. Или мы камеру вращаем. Здесь мы камеру вращаем, чтобы снять всю панораму. Смаз сразу очевидно получается. Вот его нужно снять перед тем, как распознавать, что же там камера наша сняла, какие там изменения. Ну, пока мы смотрели вот эту задачу, нас группа, которая специализируется на высокопроизводительных, очень быстрых вычислениях, и мы вот хотим добиться здесь каких-то рекордов. Ну, там есть методы Люси Ричардсона, там еще какие-то, которые долго работают.
Спасибо. Еще вопросы?
Есть стабилизированное. Скажите, насколько я понимаю, вы оперируете с RGB данными, да? RGB данные, представление цвета.
Да. В данном случае мы взяли однотонную, черно-белые серии.
Хорошо, а нету, так сказать, никаких вариантов вашего алгоритма для работы с цветоразностным и яркостным представлением цвета? Потому что тут гораздо меньше данных нужно обрабатывать, например, в формате 4.2.0.
Ну, пока нет.
И камеры зачастую именно в таком формате данные передают, поскольку, опять тут меньше просто нужно самих данных, нежели чем в формате RGB, вот в таком варианте. То есть, и чтобы не производить никаких дополнительных преобразований вот из люма и двихрома в RGB обратно. Вот.
Ну, нам будет интересно посмотреть. Я глубоко сомневаюсь, что мы увидим результат меньше 4 операций на бит, на пиксель. Мы посмотрим. Мы идем с другой стороны, пока у нас большого нет.
Ну вот можно.
Да, спасибо большое.
Thank you. Thank you. Originally, the task was to operate with the with the gray background. So RGB, no RGB, it's not relevant. And so the task was very specific. The people who so they had static cameras, and so then they kind of unmovable, and so they catch aircraft, and so then they should avoid blur. There's a commercial. It's static, but it's commercially static. So then the cameras don't move. So it's a defense probably ministry that was ordering this. So then model that you're using. Then I did here the camera. This rolling shutter. So then it's a rolling shutter when the camera moves. So different lines get different blur level. Yes, understand. Yeah, this we have it. We have this kind of special algorithm for that, but it has to do, it's right. If we watch a sphere, then sometimes they put, well, not this project, there are 4 cameras, so at different angles. It's true, and then adjustments and corrections are made. So the algorithm of calculation of adjustments, we have this. So they're implemented separately, and this we haven't had any examples of that. But we do that. It's factored in. It's factored in. But it increased the number of operations from 4 to 8, 10. This is true. Yeah, but this is This is a small constant. And so then the picture is 1,000 by 1,000 pixels at least, and so we have a lot of reserve compared to other algorithms. No, because we need just to get the highest quality. So I'm moving better from one specific case to a very fast general case. Okay. Any more questions?
Ну, один практический вопрос.
One practical question, and so then this is the wall in the shop, right? The wall in the shop, and so we with cards, so we have a lot of room, and then another one. How can, for example, if there is a good picture, to make a bad one out of a good one for archiving or making it look ancient, old photograph. So our group has been involved in obfuscation, and so we do that. But we have not yet done that. So we're not just turning good pictures into bad ones. We just no. And the last comment I'd like to make. So because this the Queen of Ace, right? So they came up. So the Queen of Spades came out, right? Ah, you're talking about Pushkin's story, the Queen of Spades. Okay, the Queen of Spades, not the Knight. Yeah, yeah. So there was a substitution, the Queen of Spades. Mr. Pushkin. So yeah. Okay, at this point, so we're done, and so that's on this cheerful note. Thank you very much.